Okay, so I'll be discussing our recent work. Okay, I'm stuck here, looks like. All right. So I'll be discussing our recently published work on chiral phase transition in 3-flavor QCD. So I will start with a bit of motivation, which will of course consist of Pisarski and Wilczek remarks, as well as the Columbia plot. Then I'll go on discussing a bit of past work. But of course, both of these points were discussed in great detail in the previous talk. So I'll be just a bit brief about these 2 points. Then I will go on discussing the universal properties near a critical point. After that, I will define the chiral observables, which are required to study the chiral transition temperature in 3-flavor QCD. And I'll give a bit of simulation details. Then I will present our results for the order parameter and its susceptibility. And then I will present the finite size scaling analysis done by us. I'll close with the conclusions and outlook. Okay, so we know in QCD for the case of NF massless flavors, left-handed and right-handed quarks transform under global independent SUNF symmetry groups. This whole symmetry group gets spontaneously broken down to the diagonal subgroup, which corresponds to the isospin symmetry which we observe in nature. And as pointed out by Pisarski and Wilczek, that the order of phase transition for number of flavors greater than or equal to 3, it depends. I'm sorry. So in this work, we are trying to see how, as a function of temperature, this spontaneously broken symmetry group gets restored. And we are looking at when number of flavors, when this NF is 3. And so the point is the order of the phase transition depends upon the number of flavors that become degenerate. And by Pisarski and Wilczek arguments, we know that this should be first order when NF is greater than or equal to 3. So this is the Columbia plot, which was also introduced by Ove in his talk. So we are approaching the problem along this diagonal. And we are trying to see if we can get the signatures of this second order critical point, or better, if we can enter this green area, which represents the first order transition region. So of course, attempts have been made in the past. People used unimproved actions. They found out that they found the evidence for the first order transition region, but the critical parameters, they turned out to be strongly cut off and discretization scheme dependent. Then the analysis was performed by improved actions, highly improved staggered Koch action in 2017 on lattices with temporal extent of 6. They couldn't find any evidence of the first order region. However, they were able to establish an upper bound for the critical pion mass, which was about 50 MeV. And for the Wilson-Clover fermion action, they also found that the critical parameters were highly cutoff dependent. They went up to n equal to 12, and according to them, the critical pion mass was about 110 MeV, and they quoted a critical endpoint temperature of about 134 MeV. So since we are talking about a second order critical point, we know that in the vicinity of a second order critical point, it is the free energy density which dominates. System behaves in a characteristic way, independent of the details of the microscopic interactions. And we can write the free energy density in this form. Here, B is the free scaling parameter. D is just the dimensions. T and H are the reduced scaling variables. So T and H depict how far away are you from the critical point. And T naught, H naught are the non-universal parameters. For that matter, TC is also the non-universal parameter, which has to be estimated. We can choose this free scaling parameter in such a way that free energy density becomes a function of one scaling argument, which is Z given by T upon H raised to 1 by beta delta. Beta delta are the critical exponents depending upon the universality class. So now, general scaling features hold for both Z2 and O2 with slightly different critical exponents. If we have a Z2 universality class, then we have to account for a non-vanishing critical pion mass. For that, we need to modify this numerator, and we need to add we need to make h. We'll take h to h minus hc. So as you will see in the next slides, we couldn't find any evidence for the first order transition region. Therefore, we'll only stick to the O2 scaling functions, and we'll put hc to 0. So now we can construct the order parameter by taking a derivative of the free energy density with respect to the symmetry breaking field, which in this case will be the quark mass. Another derivative, we will have the susceptibility of the order parameter. So there are three major important messages on this slide. First one is that the scaling function of the total susceptibility peaks at a characteristic value, Zp. So you can see in this plot that for three different universality classes, we have three different values of Zp's. Second one is that the ratio of these two scaling functions, it has a unique crossing point at t equal to tc for different values of h. You can see that in this plot that the ratio of the two scaling function, it crosses at 1 by delta for these three different values of h. Next is that this difference m minus h chi m, it does not receive any regular contribution at order h, and this way we can do a fitting for this parameter without worrying about the regular contribution, at least which is linear in h. So having introduced order parameter and its susceptibility, we need to know what are the counterparts of these two variables in the three flavor QCD. So let's start with the partition function of QCD with NF degenerate flavors. So the partition, so here is the integral over all the possible gauge links. D is the fermionic matrix. So ML in our case, we only have one fixed value of ML because all the three flavors are degenerate. And NF is of course 3. 1 by 4 is because we are dealing with the staggered fermions corresponding to each flavor. We have 4 tastes, and SG is the gluonic action. So we can take the derivative of logarithm of Z with respect to this symmetry breaking field, which in our case is the quark mass. We can get chiral condensate, and using this we can construct something called using this we can construct a counterpart of the order parameter. And well, here n sigma and n tau are just number of points in the spatial and the temporal direction. We can take another derivative of the chiral condensate. We'll get something called the total susceptibility, which is a combination of chi disconnected and chi connected. And the symmetry breaking field, like I said, maps to the quark mass. Here I will introduce like what is MS. It's just an external parameter which has been used to set the scale, and temperature goes to temperature. So some simulation details. We used his reaction for calculations and Bielefeld GPU code. We fixed the temporal lattice extent to 8, and we used 3 different aspect ratios. Aspect ratios is just the ratio of n sigma by n tau. So we used FK scale setting from 2+1 flavor to fix the temperatures for various values of gauge couplings. And our quark mass, which is ML, it is the fraction of the strange quark mass, which is used to define the line of constant physics of 2+1 flavor, which corresponds to the physical strange quark mass. So in that way, it is just an external parameter in our calculation. So we investigated 4 such quark masses, which in the continuum correspond to pion masses in the range 80 MeV to 140 MeV. And we saved every trajectory separated by 5 time units, and we used 100 random vectors for calculating the fermionic observables. And this is just a number of statistics which we require to get a good signal. You can see as the quark mass decreases, we need more and more statistics to get a good signal. So moving on to the results, these are the results of our order parameter in FK normalization. Similar to MS, FK is just an external parameter which has been used for the scale setting. So you can see an order parameter, it varies rapidly but smoothly with the temperature. And as we decrease the temperature in the low temperature region, you can see that finite size effects start appearing. So like we have 4 quark masses, and for 3 of these quark masses, we have 2 different n sigma. So you can see, for example, here, this is the lowest quark mass. So there is a split between these 2 n sigma values. Here also you see a split between these 2 n sigma values. So in the low temperature region, we start seeing the finite size effects. So as a first analysis, we tried fitting our order parameter data for several values of temperature to this ansatz. The expectation is that in the high temperature region, M should be linear in H, and in the low temperature region, it should be 1 by delta. So this inset, it shows how this exponent B behaves as a function of temperature. You can see for these, for the high temperatures, it's approaching unity, which is according to the expectation. And as the temperature decreases, this exponent also decreases, and it is it is consistent with the expectation, because it is very close to 1 by delta value for 3D auto universality class. So in that sense, we can say that we have bracketed the scaling window. So next are the results for the total susceptibility in FK normalization. So first observation is that our results are consistent with the scaling expectation. So this is our highest quark mass, this is our lowest quark mass. So as the quark mass decreases, we expect the peak position to shift to left, which is happening here. Second is that the peak height for a fixed mass. So for example, if we look at these red pentagons and these blue stars, these correspond to the fixed mass with different values of n sigma or volume. So we see that the peak height does not increase with the volume. So we can say that we couldn't find any evidence of the first order transition region. And if we look at the lowest volume of the lowest quark mass available, which are these squares, you can see that the peak gets less resolved. And we start seeing the finite size effects. We need to take into account the finite size effects which we are seeing. And how will we do that? We can add a relevant scaling field to our free energy density, and then we can bring this free energy density to this form where it depends upon two scaling arguments now. Z is same as the previous one. ZL is given by this, which will go to 0 in the thermodynamic limit. And we can add regular contributions to M and chi-M as well. So this regular contribution is nothing but the Taylor expansion in the vicinity of T equal to TC. So so now we can use these finite size scaling functions to fit data corresponding to quantities such as this ratio and this difference for various available combinations of quark masses and volumes which we have. And we can extract TC as the fit parameter. So we performed many such fits for this ratio. So by many such fits, I mean we varied the quark mass range, and we varied the regular term as well. So here I'm showing results only for two such cases. H max equal to 1 by 27 means that we included all the quark masses. H max equal to 1 by 40 means we excluded the highest quark mass. And you can see also this gray region is not included in the fit. So TC was one of the fit parameters, and we extracted the TC value. You can see here, if we exclude 1 by 27, we get a better chi-square per degree of freedom. And these fits are only when regular term is linear in TT naught. We also performed fits where we only had a constant term, and we also of course varied the quark mass range. So you can see this ratio should have a unique crossing point in the thermodynamic limit, which in this case is below the temperature range we explored. So you can see it is around like 100 MeV, and the temperature range explored by us is about 109 MeV. So, and this crossing, of course, gets spoiled by the regular contribution. So moving on to the difference, we did the same thing for the difference. We varied the quark mass range, but this did not have any regular contributions linear in H. So again here, this gray region is not included in the fit. And you can see if we remove the highest quark mass, the chi-square per degree of freedom improves. And we were able to extract the TC value here in this case as well. So after doing these two fits, we compared the results, and we realized that the parameters of the singular part of the fits from both the quantities are in excellent agreement with each other. It was, yeah, I mean, we were very happy when we saw the results that they are in very good agreement with each other within error bars. But the parameters of the regular term, they were not that strongly constrained. But yeah, I mean, that was the observation which we made. So now moving on to the third probe, which we can use to get the TC value, which is the TPC. TPC corresponds to the peak positions of the various susceptibility curves. When I showed you the susceptibility plot, it was depicted that the peak position is a function of mass as well as the volume. And to extract the TPC values, we constructed 100 bootstrap samples at the level of the gauge configurations, and we performed quadratic fits in the peak range for each such sample. We also tried to vary the number of points to take care of the systematics. After extracting these TPC values, we fitted it to the scaling expectation. So now here, see this peak position ZP is a function of ZL, which means it's a function of, now we are taking into account the finite size effects in the TPC as well. And we fitted this TPC value to this scaling ansatz. So here are our results. These squares, circles, upward triangles, downward triangles are the data points. And here also we varied the Koch mass range. The results are for when we included all the Koch masses and when we removed the highest Koch mass from the fitting. Here the x-axis is proportional to the scaling variable Q. So you can see here also the TC value which we obtain are in, they agree within error bars with the TC value obtained from the previous two quantities, and chi-square particular freedom improves if we exclude the highest Koch mass. Right, so having obtained TPC, having obtained the chiral transition temperature value from all these three quantities, let's see what our data says about the order of the chiral phase transition. So this quantity m upon chi-m at TPC is a constant which is given by the ratio of the scaling functions, and it is almost volume independent. So here in this plot, we you see we have these four Koch masses, and let's first talk about this red line. So this is the slope of this red line is described, is given by the ratio of these scaling functions. So you see it describes these two, these lowest two Koch masses very nicely. I'll emphasize that this is not as if we did a fitting to these 2 points. No, it is completely parameter free, and it seems to be describing our results very nicely. For these two highest Koch masses, we need to add the regular terms, and after adding these regular terms, we are able to describe these two data points, these highest two Koch masses as well. We also tried doing it with Z2 scaling functions, and you can see we went down up to 40 MeV of critical pion mass, and we always end up missing the data. Yeah, these Z2 scaling functions always end up missing the data. So we conclude that our data is consistent with the O2 universality class functions, not the Z2 scaling functions. Right, so I will conclude, and we varied the Koch mass range as well as the regular contribution in the finite size scaling fits to take care of the systematics. Fit parameters obtained from all the fits, we combined them and we obtained a final value of TC in the chiral limit, which is about, I would say 100 MeV. And in the explode pion range, in the explode pion mass range from 80 MeV to 140 MeV, we found no evidence of the first order phase transition. And chiral observables at finite lattice spacing show universal finite size scaling behavior, which is consistent with O2 universality class. So next step would be to take the continuum limit. In doing so, careful consideration of the correct ordering of continuum limit and chiral limit is required. It's worthwhile to mention that in the 2+1 flavor study, both these limits turned out to be interchangeable. Right. So questions?
Thank you very much, Sipat, for this very nice talk. Questions?
Okay.
Thanks. So just can you go back to the previous slide?
Sure.
So for the Z2 scaling, I mean, the amplitude, or I mean, the prefactor, I mean, is this a parameter of free prediction as well? Sorry.
Yes, it is, because it is just a ratio of the scaling functions, and these are available.
Yeah. So okay. I mean, what you're saying is that it doesn't. It doesn't agree with your data then at all. I mean,
you can say that it cannot describe the data points at all.
Yeah.
It completely misses them, and
even though the slope looks correct, I mean, the fact that the
I mean, we went down at least up to like 40 MeV, and it still misses these two data points.
Yeah.
So we can go to a very small Cork mass, and I think it will correspond to xc equal to 0 almost, if you really want to describe these two data points from Z2 scaling functions. So.
Okay, thank you.
Yeah.
Yeah, this is an order of limits question again. So it's O2 because you're staggered, right? So you have only one Goldstone.
Because we only have a remnant of
right.
chiral symmetry for the staggered fermions.
Yes, I was wondering if one could think, I'm not sure if this is practical at all, but would one expect something different if you would first take the continuum limit at fixed volumes and then do the scaling? I don't know if that would be practical, but then one should recover the larger ON group, right?
So if you take the continuum limit before the chiral limit, it depends where you are. Like, are you in the vicinity of the chiral transition temperature, or are you away from it? If you're away from it, these two limits might be interchangeable. But if you're in the vicinity of the chiral transition temperature, then you have to see, like, is it possible or not?
Yeah, I have a question concerning the size of the temperature. You say essentially 100 MeV.
Yes.
For 3 flavor. Now we have, I mean, from your group also, let's say 130 MeV for 3 flavor.
2+1.
I don't know what, I mean, there's certainly a 2 flavor value. Now, if I make the large NF interpolation, I get essentially the conformal limit at about 6, 7.
Right.
NC, NF, if I'm not mistaken. This is very low.
But it is expected that as the number of flavors increases, the temperature should go down. In the conformal limit, it should hit 0. So
yeah,
I think
but I mean, it's more 10 to 12 and not 6. I mean, if I take also the results of Maria. So have you looked at this? I'm just puzzled a bit. That's all.
Okay.
Is there any hint about the NF equal 4? Chiral transition? Is anybody? Yep. Hey. So you interpolated the quenched case from 0 to 3.
Maybe Maria has something to comment.
No, it was very, very interesting. I would like to ask you, yeah, in this respect, because this is also something I found very confusing when we were first doing this study. How do you set the scale? Because the scale setting is sort of delicate, because between 2 and 3 flavors, lambda QCD changes. So depending how you handle this, also the shape of this line may change. So that's not too trivial to do. So what you suggest is not too trivial. If you do let me say this, if you do in a trivial way and you do some sort of a scaling and you get TC over lambda QCD, TC is even increasing with NF, which seems crazy, but you can understand it. So yeah, sorry. So question is really, how do you fix the scale for this?
So at present, we are borrowing the scale setting from 2+1 flavor, and we did it using FK scale setting. We used the kaon decay constant. Like I think I mentioned this here in the simulation details. Yes, I can go over it again. So we used FK scale setting from 2+1 flavor QCD. So and also the line of constant physics in 2+1 flavor QCD corresponds to the physical strange quark mass, which is tuned by keeping the mass of fictitious eta SS prime fixed. So all our masses, like ML, are a fraction of this strange quark mass. Right, I think, yes. Right, I think, yeah. Right, I think, yeah, I discussed this with Fridjof as well. So even according to him, if we really want to see this, like if the number of flavors increase and do we see this temperature dropping, we really need to do a different scale setting. For example, yeah, depending upon like R0 or R1 or not these, not with the FK scale setting. If we want to go to higher number of flavors, yes. Yeah, yeah. Mm-hmm. Right.
Maybe we have time for one last question.
And also because just one thing, I think I wasn't very clear in the very beginning about like what does NF equal to 3 mean? So partly because this mic is very uncomfortable for me and I'm wearing a mask. So we are dealing with NF equal to 3 means that we have 3 degenerate flavors and we are approaching the chiral limit. So yeah, we are trying to see like when all of these 3 quark flavors become massless, what is the order of the phase transition temperature? And we have taken the chiral limit at the finite lattice spacing. So we are approaching the problem along the diagonal. I hope I'm making myself clear now, like what does 3 flavor mean, right?
Yes.
Okay.
So I think we thank Sivat again.